We will discuss on gasification. Gasification can also be considered to a technology which falls under clean development mechanism. Let us see how it falls into that. Gasification involves conversion of solid fuels, into gaseous fuels. The gaseous fuel known, there are several names, either say producer gas, water gas, or in general we can also call as a fuel gas. All these names, they differentiate in the composition of the combustible component of the gaseous fuel. How is it made? How is it made? We will deal with the producer gas, though we know that all other names, they differentiate in the composition. So, a producer gas is made by treating coal or coke with a mixture of air plus steam in a high temperature environment. So, I will just put it, say producer gas, or for that matter any fuel gas, is made by treating coal or coke plus mixture of air plus steam in a high temperature reactor, and as a result of this reaction, for example, if you consider coal and oxygen or air, then the reaction is, say for example, C plus O2 plus 3.76 N2, that is equal to CO2 plus 3.76 N2. Now, this reaction is highly exothermic in nature. It generates a very large amount of heat. Now, CO2 in its subsequent rise through the reactor, it reacts with carbon and forms 2CO, and this reaction is highly endothermic in reaction. This reaction is highly endothermic in nature. So, the net reaction which will occur, if we sum total the reaction 1 and reaction 2, then we get 2C plus O2 plus 3.76 N2, that is equal to 2CO plus 3.76 N2, or we can also write C plus half O2 plus 3.76 N2, that is equal to CO plus 1.88 N2. And this reaction, as I given in earlier lecture, heat of formation delta H F naught CO, that is equal to 29.6 into 10 to the power 3 kilocalorie per kg mole. That is, this reaction C plus half O2 plus 3.76 N2 is equal to CO plus 1.88 N2 is also exothermic in nature. So, large amount of heat will be generated. So, according to equation, let us say 4, according to equation 4, The producer gas, it consists of CO plus nitrogen. Now we can calculate the percentage CO, that is equal to 1 into 100 upon 2.88. 2.88 is the total number of moles of the gas which is being produced. So that is equal to 34.6%, and if we calculate percentage nitrogen, then that will be equal to 1.88 into 100 upon 2.88, and that is equal to 65.4%. So this is what the composition of producer gas. Now we can also calculate volume of producer gas. Volume of producer gas, and that will be equal to 2.88 moles into 22.4 upon 12. So that will be equal to 5.38 meter cube producer gas per kg of carbon, and this is at temperature 273 Kelvin and 1 atmospheric pressure. So this is how one can perceive the composition of producer gas when air reacts with, for example, pure carbon. Now this reaction 4 which we written is highly exothermic in nature. Now if we just calculate the amount of heat that is generated, say C to CO, it will generate of the order of 2467 kilocalorie heat will be generated on oxidation of 1 kg carbon. So this heat, if not utilized, then it will heat the wall of the reactor and this heat will go into waste. Now for example, if we take a large size reactor where heat losses will be minimum, so internally the reactor will be heated up and that may affect the lining of the reactor. So in order to compensate the large amount of heat which is produced, it is logical to use steam, and therefore steam is used. Steam is used to gasify the carbon, and in presence of steam the reaction which is there, C plus H2O, that is equal to CO plus hydrogen. Let us put this reaction number 5. Now there are several advantages of using steam and air, that is a mixture of air and plus steam for carrying out gasification. Now few advantages are, as you are observing in reaction 5, first advantage is the producer gas which is formed, is enriched in calorific value, because earlier C plus air was giving you CO, now C plus H2O gives you CO plus hydrogen. So additionally your producer gas is also containing the calorific value of hydrogen in addition to carbon monoxide. That is advantage number 1. Second advantage is that the excess heat which is produced by the reaction C plus half O2 plus 3.76 N2 is equal to CO is effectively utilized. So excess heat is utilized. Excess heat is utilized. You do not need to supply any extra heat, only the heat generated with the reaction C plus O2 is equal to CO, that is used to decompose steam and hence to enrich the calorific value of the producer gas. Third obvious advantage is the fuel gas or producer gas, it contains additionally hydrogen also. Fourth advantage is gas is enriched on per unit volume basis, on per unit volume basis. So, these are the certain advantages of utilizing steam. Now, here one precaution is to be taken. You cannot feed amount of steam indefinitely, because effectively the heat produced by the reaction C plus half O2, that is equal to CO plus 1.88 N2, that is an exothermic reaction. Whatever amount of heat which is being produced, it will be consumed by C plus H2O is equal to CO plus H2. So, by doing the heat balance, one has to supply the exact amount of steam which will satisfy the heat which is produced by the carbon monoxide reaction. So, that is the important thing, is that amount of steam fed, amount of steam fed, it must be equal to that required to absorb excess heat. Now, this is very important in using steam plus air to gasify coal or carbon or whatever you want to gasify. Now, for this purpose calculation must be done, because you are not supplying any heat from outside. It is the heat generated within the reactor is utilized for decomposition of steam, and that is important. Now, here please note, not all the steam decomposes to hydrogen. Not all steam decomposes to hydrogen. If you feed excess amount of steam, then a situation may come during the operation that the temperature drops very fast, and you may not be able to carry out any gasification. Hence, proper feeding of steam is necessary. Second is, not all CO2 is converted to CO. Now, why this is important? Because as carbon comes in contact with the oxygen, then the first product which forms is the carbon dioxide. Now, carbon dioxide in presence of excess carbon is not stable, and it immediately converts to CO. So, therefore, the temperature, the kinetics of reaction between CO2 and C, these are all the important issue to get what percentage of CO2 gets converted into CO, because the objective is to convert CO2 to CO. Now, a simple gasification process, it can be represented in this particular fashion. Say this is a simple gasification process of coke with air. Now, for example, say here supplying coke, and here the output is fuel gas or producer gas, which contains, for example, CO plus nitrogen or any unreacted carbon dioxide also. Now, the bottom, this is ash. So, here we have Hs, and Hs is a H plus carbon, and here we can supply air or oxygen. That is a simple representation of a gasification process where coke is gasified by air or oxygen. The motion is counter current. Coke is flowing downward and air is flowing upward. So, in this particular zone, let me put, this is 1, this is 2 and this is 3. I demarcate, this is, so the zone 1 we call as a combustion zone. Now, in this zone, C plus O2 reacts with CO2. Second zone, a reduction zone. And third is preheating zone. So, at a steady state, what will happen? Coke will travel downward and the hot gases will move upward. There will be exchange of heat and mass transfer. So, on account of that, coke gets heated up, it falls down in the reduction zone, the combustion zone. In the combustion zone, carbon reacts with oxygen, forms CO2, the gas goes up, gets reduced with carbon, and hence the gasification process is on. Now, if you want to represent the volume percent of the gases which are utilizing, so what I do it now, this is a combustion zone which is, if I put at 0 here, and this height of the bed if I take as h, then what I do, this distance, this height of the reactor I am representing on the x axis. So, I put here as 0 and here somewhere is h. So, I will just close down. So, what will happen? At the 0, as the oxygen comes in contact, say all the oxygen towards the end or towards the higher part of the reactor, this is the way in which oxygen will vary. It is obvious also, as the oxygen comes in contact with the carbon, here you have the 100% oxygen. So, 0 point, air contains 21% oxygen, and as the gases move up, the oxygen concentration, it continuously decreases. Now, what happens to, say for example, CO2? So, if we take CO2 concentration, it will rise up and attains a maximum value and then asymptotic. So, this is about, line is CO2 and this we can call CO2 asymptotic, that is equilibrium value which will depend upon temperature, and this curve, it falls at high temperature, because higher is the temperature, CO2 will react more with carbon and to form CO. So, if we represent now the carbon monoxide, then the carbon monoxide will go somewhere. This is the curve for carbon monoxide, and this also we can put it, say asymptotic, equilibrium, and this curve will rise up as the rise in temperature. And you all know that CO2 plus C is equal to 2CO, it is favored at high temperature. So, this particular diagram, it tells you how the gas composition, gas composition variation in air blown coke bed, nitrogen will remain constant throughout the process. Now, as we have seen that CO2 plus C, it reacts and it forms carbon monoxide. So, in fact, the residence time of the CO2 C is important. From the kinetic point of view, more is the residence time, higher will be the conversion of CO2 to CO, and this is being shown in this particular diagram. So, this shows here the effect of contact time time and temperature on CO2 plus C, that is equal to 2CO reaction. So, here it is CO which is formed say in percent, and here is the temperature. So, as said, the reaction which we are considering is CO2 plus C, that is equal to CO2CO, and we already know higher is the residence time, more will be the conversion of CO for a particular temperature. As the temperature rises, the conversion of CO2 to CO will also go up. Now, the maximum conversion thermodynamically that occur when you blow air is 34.6% as we have calculated earlier. So, for example, if we have a very say large contact time, I will say somewhere this is say 34.6, which you cannot cross thermodynamically at any temperature. So, here this is the contact time. If we say this T, that is equal to infinity. A very large contact time, of course, if you have a very large contact time, then naturally CO2 plus C is equal to 2CO will approach to equilibrium, and this line will approach at a very high contact time. Now, as you decrease the contact time, so another extreme if I take, say the contact time is very small, for example 0.1 second, just an order of magnitude. So, for 0.1 contact time, so this I say T, just a symbolic 0.1 second, you should not think, because the composition, if you want to read against the blue line, it may not tell you, but just it says that this is the maximum contact time and this is the minimum contact time. So, you see, when the contact time is very small, then you have to go for a very high temperature for reaction CO2 plus C to 2CO to take place. Now, in between, say there will be several curves depending on the contact times, this. So, if I go in this direction, say this direction, if I look at, so in this direction, increase in contact time, increase in contact time between the reactors. Now, this is the information available to us from the kinetic investigation. Now, these information are very useful from design point of view. How? Say from design point of view, because you will be operating, for example, at a particular temperature. The reactor is refractory lined. You have to decide the temperature. For example, you want to operate 1000 degree or 1100 degree Celsius, because higher is the temperature, the problems associated with temperature will also be there. So, once you have decided the temperature, then optimization of residence time is important. Then you have to choose the reactor dimension, because higher is the height or higher is the height of the bed, the contact time between CO2 which is formed at the combustion zone with carbon is more. So these factors are to be optimized. So this particular diagram tells you that here residence time is important. Residence time between CO2 and C, that is the most important. You can have higher residence time by having a larger height of the bed, but well, how high? So these factors are to be optimized in order to design the reactor, size of the reactor, diameter of the reactor, height of the bed. All these are important issue for conversion of CO2, which is formed due to oxidation of carbon immediately as it comes into contact with air, and its subsequent conversion to CO is more important, because whatever CO2 that goes along with the fuel gas is unutilized and it does not contribute anything to the calorific value. Generation of large amount of heat, and heat is utilized by blowing steam. For example, in the reaction, say C plus H2O, that is equal to CO plus H2, or this reaction can occur C plus 2H2O, that is equal to CO2 plus 2H2, and ultimately CO2 reacts with carbon, that is equal to 2CO. So let us see the decomposition of steam in coke bed. Decomposition of steam in, for example, coke bed. So this axis is, say, percentage of H2O decomposed. So we take 0 to 100 and 0 to 1, and I want to close down here. Now on this y axis I have moles H2, CO or CO2 formed per original mole of H2O. So this line, it represents the formation of hydrogen. Naturally, more steam decomposes, more H2 will form. Now about the CO2. So CO2 attains a maximum, and then on 100% decomposition it drops to 0. That is the variation of CO2. Now the variation of carbon monoxide, this is the variation of carbon monoxide. So that is what the various proportion of H2, CO and CO2 are available in the producer gas on decomposition of steam. Now say in making producer gas, air and steam are blown continuously. Air and steam are blown simultaneously and continuously through the bed, through the fuel bed, coke bed or whatever. Now it is a dynamic process. Air and steam are blown and coke bed is there, and depending on the residence time the reaction takes place, and depending on that the producer gas the composition of the various components in the producer gas are influenced. Now, if I want to show the principal reactions, and reaction zone when a mixture of air plus steam is passed up a bed fed with raw coal. So, I will show the various zones here. For example, I am charging coal. At a steady state, coal flows downward and the gases move upward. Now, the zones, for example, this is a ash zone. Ash continuously is removed. Then we have, this is the oxidation zone. Or in short, we can also call a combustion zone. Combustion zone means here carbon is completely burned to CO2. So, as such, the reaction in combustion in this oxidation zone consists of C plus O2, that is equal to CO2. It is very hot gas, it moves up, and then we have the second zone which is called this one, which is this is the primary reduction zone. Primary reduction zone, and in the primary reduction zone the reactions which will occur C plus H2O, that is equal to CO plus H2, or C plus 2H2O, that will be equal to CO2 plus H2, and CO2 plus C, that will be equal to 2CO. So, the primary reduction zone is very important, its height, the residence time, because the CO2 will move up, it will react with the carbon and steam which are there, and these reactions will occur. On the top of the primary reduction zone, we have a secondary reduction zone. So, this one I can put it here, say for example, this one is secondary reduction zone. Secondary reduction zone, and in the secondary reduction zone, the whatever left CO2 can also react, it may form 2CO, and the CO may react with H2O, that can form CO2 plus hydrogen. Now, on the top of it we have this particular zone. This is the drying and carbonization zone. Because the coal is charged at 25 degrees Celsius, it gets heated up by the hot gases which are rising up. On account of this, in the top portion of the gasifier, the volatile matter cracks, decomposes, and the methane or the tar which are produced, they join the producer gas. So, that is what the top gas, this is what the drying and carbonization here, and this one, or rather this one, is the producer gas space. So, from here the producer gas is discharged, is cleaned and fed for its subsequent use. Now, if we use the coal, then the producer gas will consist of, for example, CO, then CO2, H2, it may have nitrogen, it may have methane, it may have tar, soot and ashes. Now, there are certain issues with the gasification by when you use coal. One, the ash formation and the temperature of ash formation is very important. That is, fusion and clinkering of ash may occur. And second, when volatile matter is removed from coal, then tar formation also occurs. Though tar is a very high calorific value, but then it has to be removed from the gas which is being formed. If you use coke, then the formation of tar and the methane which occurs because of the decomposition of volatile matter may not occur. Similar is the case with anthracite. Anthracite does not contain any volatile matter, so the formation of tar will not occur, and as such the formation of methane may also not occur. So, we have seen now the science of gasification and saw various reactions, various requirements for conversion of solid fuel to gaseous fuel. We have seen residence time is important, the amount of heat which is produced and its utilization by blowing of the steam is important to take care of the excess heat which is produced. Now, all that we have done from the science. Now, the important thing now how it is done in practice. So, technology of gasification, there are certain important points that are to be noted for developing a technology for gasification. One, we have to see how coal is fed. That is, feeding of coal is important. Now, you have to deal with few tons of coal, how you are going to feed into the system. Second important thing, as you have seen, ash is also formed, and the coal, if it contains 20% of ash or higher amount of ash, then a large amount of ash disposal will be there, and accordingly while developing a technology you must consider how you are going to dispose the ash. So, ash disposal is important. Ash disposal mechanism is also important, how you are going to dispose the ash during the process. Third important thing is that how a mixture of air plus steam is supplied. Air plus steam supply, how it will be done, that is also to be seen. Then fourth, the discharge of fuel gas, discharge of rather producer gas, or you may call fuel gas, how you are going to discharge and what is its ultimate use. Is that the gasifier apparatus is nearby the consumer or it is away from the consumer, and then what is being planned from the products of gasification, which contains producer gas, which contains tar. Tar is again a very high caloric value product. Soot, which again contains a very high amount of carbon, and so on. Fifth important point is the maximization of residence time. Maximization of residence time. Now, here the flow velocity of the gases which are rising upward, that is important, but once you decided the size of the reactor, then the velocity is also fixed, and hence the residence time is also fixed. However, a little bit you can influence by having coke bagged. So, following these technologies, there are several gasifiers have been developed. I will just describe few. For example, if we take a, this is a sort of a fluidized bed gasifier. Fluidized bed gasifier at atmospheric pressure. or in short you can call this is a atmospheric gasifier. Now fluidized bed gasifier means the coal which is here is in the fluidized state. Say that is the coal bed. Now in this particular fluidized bed gasifier, the gasification temperature is 800 to 850 degrees Celsius. Lignite and subbituminous coal are used. The producer gas consists of CO, say 44.4%, hydrogen 36%, CO2 15.7%, nitrogen 2.3%, CH4 1.5%, and this gas has a calorific value, say gross calorific value is 2600 kilocalorie per meter cube. This is a typical example. The values here and there may vary depending on the book from you take it. Now in this particular gasifier, this is the system for charging the coal. The coal is fed into the gasifier by a screw mechanism. The screw moves, and as the coal falls on the distance between the screws, it is fed into the gasifier. Now here you see the mixture of oxygen or air is passed, steam is mixed, and it enters into the, say, gasifier. This is here a mixture of air and steam, or oxygen and steam. When oxygen is used, the nitrogen content will be very low. If air is used, then nitrogen will be there. So here in this particular gasifier, this is a path for secondary air or oxygen. So here also some amount of oxygen or air is blown, so that the CO2, so that any leftover carbon gets also gasified. So this is a one type of, say, a gasifier. Here the coal is fluidized. You can have fixed bed gasifier also. Now in another, for example, if you see another, say in a copper Todt-Zach process, here pulverized coal is gasified. Pulverized coal is gasified, and the gasification temperature is very high. Gasification temperature is say 1600 degrees Celsius. Product gas which is discharged at around 1000 to 1300 degrees Celsius. Now remember, when you have very high gasification temperature, then ash will be in the liquid form, the slag will form. So accordingly, the disposal of slag is also an important issue. The composition of producer gas is carbon monoxide 53.3%, hydrogen 31.1%, and CO2 plus H2S, that is 12.2%, and accordingly his gross calorific value is 2670 kilocalorie per meter cube. This is another method of gasification. Somebody uses fluidized bed. Here a very high temperature is used. Now still another gasifier that I want to say is about the Lurgi pressure gasifier. Lurgi pressure gasifier. Now this gasifier is unique in its operation. It operates at a very high pressure and utilizes the reaction between C plus H2, that is equal to CH4. So in a Lurgi pressure gasifier, the coal is gasified at a very high pressure and utilizes the effect of pressure on this reaction. Say C plus 2H2, that is equal to CH4. Now this reaction, there is a volume decrease. So if you increase the pressure, more amount of methane will be there in the producer gas, and methane has a very high calorific value. So this is also another type of gasifier which works at a high pressure. Now in this Lurgi pressure gasifier, the hydrogen content can go as high as 50%, carbon monoxide 35%, and CH4 can go up to 15%. Now this reaction C plus 2H2 is equal to 2H4 is equal to CH4. This will occur at around, for example, 20-30 atmosphere. So all that you have to design a reactor which can sustain that high pressure. So these are all the, say, important issues in this case. Now for example, here say 1 normal meter cube gas, it may require 0.85 kg coal, 1.4 kg steam, and 0.21 normal meter cube oxygen are required. Gas will have a gross calorific value of the order of 3900 kilocalorie per normal meter cube dry. So as such, there are many different type of gasifier, because this is in fact a technological issue. There cannot be one method. There has to be several different methods also. This is all about the science and technology of gasification. So you have seen that the producer gas, it contains CO2, CO, H2, H2O, N2, SO2, hydrocarbons, soot, tar, and so on. Now by way of certain problems, I will illustrate the various calculated values. Now for example, I give you one problem. Say you are required to calculate, say for example, you calculate the composition, say in volume percent of an ideal fuel gas produced by complete gasification of carbon by dry air. Take 1 kg carbon as basis. I already gave you the answer. The answer is 34.6% CO and rest is nitrogen. So you can calculate and see that you get the answer, though I have illustrated in the lecture. You can also see that you can calculate. This is the part A. Part B, now determine the calorific value of fuel gas that is produced in 1A. C, you also perform the calorific value balance, that is how much is the input of the calorific value and what is the output, that is what fraction of the original calorific value of carbon is available in the product gas. Now, say here the answer for 1B is the calorific value of fuel gas, that will be equal to anyway you can calculate and see that the answer for question for 1C, that will be around 69.55%. 69.55% of the original calorific value of carbon is available in the producer gas. Now, to calculate the calorific value of the carbon, you will be using the Dulong formula. Since it is a pure carbon, so just for information, calorific value of carbon, that will be equal to 81 into 12 into 100. That will be the calorific value of carbon in kilocalorie per kg. About the calorific value of fuel gas that is produced in 1A, so you have to calculate the amount of producer gas, that already I have calculated in the lecture, and from the heat of combustion of CO and hydrogen, you can calculate the calorific value of the fuel gas, and then you divide by this calorific value of carbon, then you will get the what fraction of original calorific value of coal is available in the product gas. So, this is how you will be solving this particular problem. I will give you one more problem, that is second one, you calculate what percent of calorific value of carbon in a gas of 50% CO plus 50% hydrogen. All that you have to take now here, 1 kg mole of carbon react with H2O, you get 1 kg mole CO and 1 kg mole hydrogen. So, you will calculate the calorific value and the answer you will be getting around 129%. Now, you have to account for why there is an increase in the calorific value of the fuel gas, because it is not 100, it is 129%. That is, you are getting in the product gas calorific value more than that of carbon, and this is obvious because you are producing hydrogen. Now, because of the gasification in presence of steam, extra amount of hydrogen is added, and as I said in the lecture, it increases the calorific value, and you are seeing the product gas which is forming, it has a calorific value higher than that of carbon. Calculate, get a feel and feel good.